Right, good morning. Hi guys, and this time around still in numerical methods, we're going to look at errors. When we say errors, I have made an error. It means that there is something that has not gone right. So when we say errors or an error, you're looking at the difference between the exact and the inexact. Difference between exact and inexact values, right? So it's saying that an error, in simple terms, is the difference between exact and inexact values. So as you program a machine to do something, you find you've done an error, okay, or something that is deviating from the original or from the exacting value. So we shall always use small letters or italics to denote inexact values, and we shall be using capital letters for exacting values. Okay. For example, an error in X. An error in X is either denoted by you can denote it by delta X or delta small x, still that is it. Okay. And this is always given by delta X is equals to the accurate or the exact value minus the inexact value. So that one will always give us an error. So we are going to cover the details. We're going to cover the details as we keep going on. So we need to know the types of errors. The types of errors are three, right? There are three types of errors, and we've got what we call a random error. Now, a random error, when we say this is a random error, we're trying to mean that error which arises as a result of human or machine nature or machine failure. You may find that maybe one was supposed to print like 50 copies of papers, but because maybe the machine has failed somehow, it has printed 49. So it has made an error in that. Or you may find that instead of someone writing a good amount of money, like a real amount of money, you have missed out a zero. So that one is, it can be due to poor reading, due to poor measurements. You can go on a wing scale and you realize that instead of maybe talking of 50 kilograms, you are measuring better and you're saying 49.8 or 49 point something. So a student can read like 42 as 24. Those are errors which are random, okay? So they can just be minimized by those machines or those individuals improving on their efficiency. So these ones, we do not look at them too much. Then two, we've got what we call rounding off errors. Rounding off errors. When we talk about rounding off errors, this one comes in as a result of approximating the true values, okay, of different numbers. You approximate. For example, if we say, if I say round off, I can say round off. Maybe 1, 2.2456 to 3 decimal places. By reducing the number of decimal places, you're already making an error in the number, because this one would be 2.246, because when we are rounding off, the third value, if it is the third decimal place is affected by the preceding value. So if this is 6, then it will affect this. So this is the 3 decimal places we are talking about. etc, even if you have 0.01578, when they wanted to 3 significant figures, a significant figure, 3 significant figures. So this is going to be 3.02. For a significant figure, we count those values. We count those values which are significant, meaning that in this case, 3 is significant, 0 is significant, 1 is significant. But if I say round off to 2 significant figures, the zeros before decimal point are not counted as significant figures. And also, if this one is a 0 starting, and then after a point there are zeros, those zeros are also not counted. In other words, this one would be 0.0049. These are 2 significant figures that I'm trying to mean. But if you say like 1.0, I'm assuming if you say 1.0, these are 2 significant figures because you didn't begin with a 0 here. If we say 0.10, these are 2 significant figures because after a 0, after a point, sorry, you have a significant figure. So the following one is also a significant figure. So these are what we call the rounding errors. By reducing a number by some decimal places, you have already changed its accuracy. Then we've got what we call truncation errors. Truncation. When we truncate, here we terminate at some point. We terminate here. It is when an infinite process is terminated at some point or appropriated by a finite one. So in this case, when we say truncate, you just terminate the point. So if we say truncate, you can say truncate. Truncate is to terminate. If I say truncate 1, 2.4567 to 2 decimal places. When you truncate this one becomes just 2.45. After a point, you count 2 decimal places, irrespective of what they would have caused. So you disregard what this one would have caused. So you just write them without rounding off. Rounding off when a figure can be increased, you increase it. But for this case of truncating, there's nothing like changing of figures. So if we are truncate 0.6666 to 3 decimal places, you just count 3 decimal places. So it would be 0.666. Okay. etc. So that is what we call, those are what we call errors. Types: random, rounding off, and truncation errors. So allow me take you very fast to what we call the error bound. Let me take you to what we call the error bound. When we say error bound, so when we say an error bound, this is an error. Okay, this is an error obtained by approximating the exact value by the inexact value. Error obtained by approximating exact value by inexact value. So that is what we call the error bound. And mathematically, error bound is always equal to 1/2 of maximum value minus minimum value. We get a half of maximum value minus minimum value. Then also another aspect that we shall be interested in this area is getting the range of values within which a given value lies, within which a given value lies. A range of values within which a given value lies. So when we say range of values within which a given value lies, we obtain this by subtracting and adding the error bound to the working value. In other words, range of values is equal to minimum value less or equal to working value, which is less or equal to maximum value. So one can write it like this, that range of values is minimum value less or equal to working value less or equal to maximum value. We're going to look at examples how we do this, and where in this case the minimum value is obtained by minimizing the function, and the maximum value will be obtained by maximizing the function. So we shall look at how to maximize the function, and we shall look at how to minimize the function, right? All right. Then or one can say that the range of values is equal to we were saying that, or one can say that a range of values is equal to working value plus or minus the error bound, or one can say range of values is equal to minimum value put a comma, then maximum value. So that is what we would look at. That is what we would have. Now, we are going to look at the details of all these with examples in the due course. Now, let's first look at the error bound in addition. We shall have error bound in subtraction. We shall have error bound in multiplication and error bound in division. So let's say error bound in addition. So when we are adding two or more values here, the maximum value is always obtained by maximizing the values, and the minimum value is always obtained by minimizing the values. For example, when we say, I'm saying that we obtain the maximum value by getting the exact value, and we add the maximum error, then we get the minimum value by getting the exact value, then we subtract the maximum error. whereby we are going to get our max, because everywhere we are talking about maximum error, maximum error. So what is that maximum error? Maximum error is a half of 10 power negative n, whereby the n is equals to the number of decimal places. Right? Number of decimal places. So that is what we can have for that particular case. That is how we shall be getting our maximum error. Then we substitute here, we get the maximum and the minimum values. The same applies with error in subtraction. When we are talking about subtraction, the maximum error, the maximum value is always obtained by maximizing the first value and minimizing the second value. And the minimum is obtained by minimizing the first value and then maximizing the second value. All right, so let's do some example here. Let's do some example. Given that A is equals to 1.652, B is equals to 9.78. Find the error bound of find the error bound of 1 A plus B and 2 is A minus B. Let's do the solution. Now, for Roman 1, where we are looking at A plus B, we are going to first get the maximum value we say that the maximum value for addition, we get the exact value, we add the maximum error, okay? So the maximum value is, rather the exact value for A, because it is A plus B, so we shall have A, which is 1.652. We add its maximum error. Maximum error, one may not need to compute all this, it may be tedious. So just count the number of decimal places, 1, 2, 3. Those are 3 decimal places. So you say 0.000, then you put a 5, because it's a half of that. So we have 0. The number of decimal places, then a 5. That is for A, that is the maximum value for A. Then plus, we are adding a B. So the exact value of B is 9.78. We add its maximum error. You count decimal places, there are 2, so you will say 0.00, then 5. So this one will give you 11.4375. So that is our maximum value of A plus B. Then we get its minimum value. Its minimum value will be obtained as, to get its minimum value, we are going to have minimizing, it will be of course, this was A maximum, this was maximum of A plus maximum of B, B maximum. So here it will be A minimum plus B minimum, since we are adding. So the minimum value of A is obtained by getting the exact value, 1.652, minus the error, maximum error, 0.0005. Then plus B, 9.78 minus 0.005. So here with the minimum value, you subtract the maximum error. So when you work on that, you're going to find yourself having 11 0.4265. So we said that to get the error bound, we take a half. Error bound is a half of maximum value minus minimum value. So this is going to be equal to a half of maximum, which is 11.4375 minus 11.4265. So it will be a half of that, which will be 0.0005. So this is what we call the error bound. This is what we call the error bound. Then for the case of 2, for the case of part B, or Roman 2, they want us to get the error bound in A minus B. But remember, our A is 1.652. And our B is 9.78. So to get error bound, we need to first get maximum values and minimum values. So we need to first get A minus B maximum, the maximum value of this. So this is going to be equaling to, when we need the maximum, if we need a maximum value, now remember we are subtracting, it means that we need to have this one as maximum and this one as minimum, so that we get a big number, we subtract a smaller number. That is when we can keep with a big number. So it will be A maximum minus B minimum. So here you don't just add, no, you maximize A, you minimize B. That is when you can get a maximum value overall. So A maximum will be 1.652. When you're maximizing, we add, so it is going to be 0.0005. Count number of decimal places, then put a 5 at the end. Then minus B minimum. B minimum, we shall subtract now 9.78. We subtract 2 decimal places with a 5. So the whole of this one will bring it to a negative value of 8.1225. This is the maximum value. Then we go ahead to get minimum value. If we need A minus B minimum, to get minimum, if we need a small value, it means that A should be small, you subtract from big. When you get small and you subtract from big, you get a small value. So we shall say A minimum minus B maximum. That one will give us a minimum value. Because if you have something small and you subtract something big, you get something small. So A minimum will be 1.652 minus 0. Then minus B maximum. For B maximum, we shall have 9.78. We add 0.005. So this is going to give us negative 8.1335. And in case, only that these ones don't need we are not dealing with addition, or rather subtraction, or multiplication or division, but we avoid rounding off unless we are told to do so. So here what you do, here what you do, after getting the maximum values and the minimum values, you go ahead to get the error bound. Remember, we said that the error bound, or the error bound, is the half of maximum value minus minimum value. So it is going to be a half of maximum is negative 8.1125 minus negative, which will go to plus, of course, 8.1335. So this one will give you 0.0055 as your Euler bound. So this is how we get Euler bounds in addition and subtraction. And allow me go direct to Euler bound in. Allow me go to Euler bound in what we call multiplication. So Euler bound in multiplication. Euler bound in multiplication. So now for this case, if you're given values A and B, assume we are given values A and B, all right? The maximum value in AB or AB maximum, to get the maximum value of this, we maximize everything. We shall maximize A and then we multiply by the maximum of B. But if we are to get the minimum value of AB, you must minimize everything. So it will be A minimum times B minimum. It will give you AB minimum. For example, one can say, find, example, I can say find the Euler bound in AB given that A is equals to 4.617 and B is equals to 3.65. Okay, so if you have that, how do we get Euler bound in AB? So you first need to get the maximum value. Or what you can call AB maximum. So to get the maximum value, we say that we maximize everything. So it will be A maximum times B maximum. And this is going to be equal to A maximum. We get A exact 617. We add its maximum error, which is 0.000, 3 decimal places, then a 5. Then it times for B, the value you have 3.65. You add a maximum error 0.005. So this one will give you a maximum error. Rather, will give you an error of here is 4.6175 times here it is going to give you 3.655, and on multiplying those ones you get 16 point. You write as many decimal places as you can, 8769625. Since we've not been told the decimal places they want us to record in, just write to minimize errors, the topic itself. And from here, we go get the minimum value, or what we call the AB minimum, and we say that we minimize everywhere, so it is going to be A minimum times B minimum, whereby A minimum is the 4.617, right? If we are minimizing, we subtract the maximum error 0.005, then times B minimum shall get 3.65 minus 0.00. 5. So this is going to be 4.6165 times here the error is 3.645. This generally gives you 16.8282. Okay. Actually, it is 828.52745. So that is the minimum value. Then to get the error bound, the error bound is going to be equal to a half of maximum value minus minimum value, which is going to be a half of shall have a half of 16.876965 minus 16.82852745, and this one on operation will give you an error bound of 0.024217525. Make sure that your calculator is capable of getting you this answer right. So to all viewers, I want you to do this. I want you to do this error bound, given that A is equals to 4.617 and B is equals to negative 3.65. Find the error bound. In AB, find the error bound in AB. So that is our question that we should do, and maybe we see. Let's see what you will get. Regardless of the negative, the logic keeps the same. So we're going to do that, and maybe we see what you will get. Then let's look at error bound in division. Error bound in division. So when you're having values A and B, okay, the error bound in division of A over B, rather, let's say maximum. If you have to get maximum value here, it means that the numerator is big, the denominator is small. So to get the maximum here, we need to have A maximum, we divide by B minimum. This one will always give you the maximum error. And to get the minimum value, A over B minimum is going to be, now to get minimum, it means that the numerator is small and the denominator is big. When you get a small number and you divide it by a very big number, you get the general small number. For example, given that A is 1.26 and B is 0.435, let's find the error bound in A over B. Error bound in A over B. So here, we need first get the maximum value. Let me take you through that chap very fast. So here, the solution would be, we need to get maximum value And to get maximum value of A over B, we shall have A maximum, which is 1.26. We add an error 0.005. We divide by the minimum value, where we shall have minimum of B. So it will be 0.435 minus 0.0005. All right, so this one will give you the minimum value as 2.911392.405. So that is the maximum value. Then we can get the minimum value. To get minimum value, we minimize A over we maximize B. So minimizing A would be 1.26. Minimize by subtracting its maximum error 0.05 over maximum of B 0.435. We add to get the maximum 0.0005, and this one will give you 2.88174521. So we can get the error bound using the method we've been using. So the error bound will be equal to half of maximum value minus minimum value. And this is going to be equaling to a half of maximum value, 2.9911392.405 minus minimum, that is 2.88174521. And on computation, this one is going to give you 0.0. Since they didn't tell me the decimal places, 0.01482364.2. So if they have told you where appropriately they want you to record the number of decimal places, you do as required. So those are that is what we call the error bound. Error bound. Now I want us to do some of the questions that involve range of values. Then after that, we go to error propagation. So let me get some of the values, some of the questions that have or that require us to state the range of values, within which the values lie. And here comes a question. Let's first do this question, then I take you forward. Here comes a question. Given that limits, range of values, within which some variables or values lie. So here we are automatically going to do examples. And example number one, given that y is equal to 1 over x plus x, and x is 2.4, correct to one decimal place. Find the limits within which y lies. So to get the limits here, within which y lies, you need to Let's first get an error. So a solution given x as 2.4 means that the error in 2.4 is, we say that it is a half times 10 to the power negative n, where n is the number of decimal places. So a half times 10 to the power negative 1, which is 0.05. Or without just moving this far, the error you can see, since it's one decimal place, says 0.0, then 5. So then we shall get the maximum of y and minimum of y. So maximum of y, that is y max, is going to be equaling to, we shall maximize everything here. We shall maximize everything. So you can rewrite this one by saying x plus 1 over x, which is okay also. So here we shall maximize. Since we need maximum, then it means that this one, 1 over x, should be minimized, so that we have, it is the same as x plus 1 over x. So if we need a bigger value, because if you maximize this to be very small value, so we shall minimize this so that we get 1 over minimum. 1 over minimum will give us a big thing. So we shall have x maximum, this will be maximized, while the whole of this will be minimized. So we shall have 1 over 2.4 minus 0.05, so that we minimize it. Then plus x maximum to be 2.4 plus 0.05. This one will give you a maximum value. So it is going to be 1 over 2.35, then of course plus 2.45 here. So this one will bring you to 2.8755. That is the maximum value. Then we get y minimum. Now to get the minimum value, we shall minimize this, and also now this one, it will be 1 over maximum. So that gives us a very small value. Okay, so it is going to be y minimum is equals to 1 over, now we shall maximize 2.45, okay, 2.4 plus 0.05. Then of course plus, now this one we shall minimize it. It will be 2.4 minus 0.05. So this is going to be 1 over 2.45 plus 2.35, which is 2.7582. But remember, when we are stating the limits, we say therefore the limits are, begin by stating the minimum, comma, maximum. So 2.7582, comma, then the maximum 2.8755. So that is how we state the limits, or that is how we get the limits. Allow me do some other question. Related to this, you can have x, our number 2 is, if x is 4.95 and y is 2.013, each rounded off a given number of decimal places. Calculate the limits within which xy is expected to lie. Give your answer to 3 decimal places. Give your answer to 3 decimal places. That is the question. And when such a question comes, it has to be the easiest to be attempted and very fast. So here, what you need to do, if they say calculate the limits, just know that the limits are equal to minimum value, maximum value. So you need to first get the minimum value. To get minimum value of xy, we are looking at xy. So we minimize everything. Okay, if we are to get minimum value, we shall minimize everything. So we shall have x, we shall minimize x, so it will be 4.95. We subtract the error 0.005. Number of decimal places, then 5. Then we multiply the minimum of this, which will be 2.013 minus the error 5. So this is going to give you 4.945 times, if you subtract this, you get 2.0125. So the minimum value is 9.9518125. But if we had to go with the decimal places needed, it will be 9.951. 3 decimal places. Then 52. Then you do the same for the maximum. For the maximum value, you're going to maximize all. So it is going to be x maximum, it will be 4.95 plus 0.005, then times y 2.013 times plus 0.005. So this is going to be 4.955 times 2.0135, and this one will give you 9.9768925, which is the same as 9.977 in 3 decimal places. And therefore, you conclude that the limits are minimum 9.952, comma maximum 9.977. That is how we get the minimum values. As simple, actually, that is how we get the limits. As simple as that. So questions are too many, and we cannot finish all of them, but I really wanted to show you how we get these values. The same applies. Let me do the final question. Let me do the final, then the rest will be yours. You have A given numbers A 6.341 and B 2.6 have been rounded to a given number of decimal places. Okay, have been rounded to a given number of decimal places. So determine the interval within which a squared over b can be expected to lie. Record your answer to 3 decimal places. Can be expected to lie. Record your answer to 3 decimal places. So, here what you do, first get me a squared over b minimum value or maximum value, whatever you begin with. A squared over b maximum. If we need maximum, then it means that we shall maximize up, we minimize down. So it is going to be a 6.341 plus its error 0.0005, then squared. That is maximum value, then squared out of b minimum. B should be minimized, that is 2.6 minus 0.05. So this upper thing is going to give you 6.3415 squared over 2.55, and this is going to give you 15.77044. That is the maximum value. Then you look at the minimum, a squared over b minimum. To get the minimum, it means that if we want the minimum, the upper thing is minimized and the lower thing is maximized. So it is going to be 6.341 minimize 0.0005 squared out of, we maximize this, so it is going to be 2.6 plus 0.05. All right, so this is going to be equal to 6.3405 whole square, then over 2.55. We are maximizing, so it will be 2.65. Since we are minimizing and we've added, it is going to be 265. Then here, the answer is going to be 15.17054. Now, the interval, you conclude and say the interval is minimum, comma, maximum. Minimum is 15.7. This is maximum. So minimum is 15.170. Is it 7071? Because they needed 3 decimal places, comma, 15.770. Or one can get the interval by writing, it would be easy, interval is 15.171 less or equal to, there you have to first compute the exact value by putting the exact values direct. 6.341 squared over 2.6. You get, so here you compute the exact value, put it, then less or equal to the maximum, which is 15.770. So still this one would work. So you realize that in all cases, when this number is brought on board, these marks have to be picked very, very well. I'm looking for the number to leave you with. Okay. This is the number I'm leaving you with. Given that x is 2.68, 0.9. Around it to a given number of decimal places. Around it to a given number of decimal places. Find the interval within which the exact value of x over y is expected to lie. It is always awarded 7 marks, so you try doing your best and see how you can do it. So the range of values, you just say minimum value, comma, maximum value, put in brackets. Or you can look for the working value and you continue, but still the same answers are going to be entertained. Let me give you also this brainy check. It's 1, 2. The brain check is that obtain the range of values within which the exact value of 15.36 plus 27.1 minus 1.672 over 2.36 times 1.043 lies. So that is the question I want us, those are the 2 questions I want us to do so that we be on the safer side to go ahead. Wish you all the best. Let's meet in error propagation.